Okay, so new topic for today. Kinda, sorta new topic. It's really the same stuff over and over again, right? We've been doing a lot of these same theorems where we follow the same pattern and we get an analogous result, just in a different context, right? So, just like we've done in the fundamental theorem of calculus, just like we did with the fundamental theorem of line integrals, just like we did with Green's theorem, right? We're going to identify in a new context something that's computed on the boundary, right? But we're going to reinterpret it as accumulating over the interior, right? So it's computed on the boundary, but it accumulates over the interior. Let me remind you. So computing on the boundary with the fundamental theorem of calculus, we're talking about how much the function changes. If you want to know how much a function changes between here and here, you plug in those boundary points and subtract. The calculation is done on the boundary, right? With the fundamental theorem of line integrals, same thing. With Green's theorem, well, now a little different. With Green's theorem, we're talking about circulation, but critically, it's circulation that goes around the boundary, right? So it's still a computation on the boundary, even if it's not actually still change, but it's still a boundary calculation. And in all of those cases, we viewed that as accumulating over the interior. Change accumulates because the total change is the sum of the little changes, right? And then we drew a different picture, dimensionally appropriate. Green's theorem observes that circulation can be viewed as an accumulation of little tiny circulations in the interior, right? Okay, so this is the one of the big unifying ideas of all of these theorems, including Gauss's divergence theorem. And again, there's one more to come after Gauss's divergence theorem. First unifying property is that something that's computed on the boundary, we realize it as actually accumulating over the interior. Okay. Next, the little pieces of quantity that we're interested in. We observe that that little piece of quantity can be viewed as something times size. In other words, that there is an associated notion of density. Right? So we've seen this first. We saw this with mass. Right? So this is just, I know I've said this a million times. I'll probably say it another couple hundred. Right? But I think it's an important idea. Mass is an accumulation of little pieces of mass. Mass accumulates. Right? Well, likewise, that little piece of mass relates to a little piece of volume in the sense that there is this notion called density, or that I would prefer to be more specific and called mass density. If you're looking at an accumulation of mass, the integrand is mass density. Well, likewise, when you're looking at change density. Right? And with Green's theorem, when you're looking at circulation density. Right? So there's an associated notion of density. Okay, so these are the big two ideas. We just have to figure out now, let me tell you how, in what context we're going to try to apply these exact same ideas. So here it is. We're going to look at a three-dimensional context. And there's a domain with a boundary. In all the examples we've talked about previously, a curve with boundary points, a two-dimensional region with a boundary curve. It's always a region and its boundary. And here, we're going to look at a three-dimensional solid that I'll call R. Now I appeal to your geometric intuition. If you have a three-dimensional solid, right, some chunk, what's the boundary of a three-dimensional solid? Well, it's a surface. That's just what the surface is, what a boundary of a solid looks like, right? So we'll call that the boundary surface. And I hope I have said this previously. If I haven't, I'm sorry. I apologize. But this little symbol here, just as a reminder, that means boundary. And it is, in fact, the exact same symbol that we use for partial derivatives, right? There's a kind of a sort of a point of view there, but I don't want to go off on a tangent. But anyway, that just means boundary in this context. Okay, so we have a boundary. We're going to talk about something that's computed on the boundary, and we're going to observe that quantity, whatever it is going to accumulate over the solid interior. So what is the quantity? Well, not change, and it's not circulation. Here, the quantity of interest, we're going to look at flux. Now, the quantity computed on the boundary. So, just to emphasize, I'll very often call this boundary flux. And of course, we have talked about fluxes through just generic surfaces. Not every surface is a boundary of something. So, I mean, it's a little ambiguous, I suppose, if I were to just say flux. But since in this context, we're always talking about boundaries, sometimes maybe I'll just say flux. And it's, should be understood and implicit that, of course, I mean boundary flux. We're talking exclusively about boundaries. Okay. Then there's the question of which way, right? There's always a question if you're talking about flux through a surface. You mean flux that way or flux this way? Which is the positive direction for fluid to be going through the surface? So there is a convention on this, just like all other conventions. Remember, if you have a curve with, let's say, a starting point here and an ending point here, well, you always take the positive value of the function over on the ending point, and then you subtract. So the negative value at the starting point. So positive at the end, negative at the start. That's a convention. It's arbitrary. Whatever. With two-dimensional regions, solid two-dimensional regions, talking about the boundary curve, we made a arbitrary convention. And again, going around just talking about outside boundary curves. Always counterclockwise. Or to be more precise, always move in the direction such that the region is on your left. It's arbitrary. So likewise, we're going to make an arbitrary convention here with solids. This is the choice that everybody else makes, so let's just get on board. It doesn't matter. I mean, if it doesn't matter, you might as well be consistent with everybody else. Right? General rule of thumb, I don't advise expressing your individuality when it comes to mathematical conventions. I think it's a bad idea, right? Just get on board, right? Avoid confusion. Here's the convention, arbitrary convention, outward oriented. So that is what we call the positive direction through the surface. So that said, notice over here. Notice the fluid is going inward through the boundary. So that would be negative flux overall happening on that side of the surface. Whereas over here, we're talking about outward flux, that is positive flux. Okay. All right. Okay, so this being said, everything from here on out is going to be a repetition. Not everything. The strategy that we're going to apply is going to be pretty much a repetition of the strategy that we applied to do, let's say, Green's theorem. So we're going to ask questions here. Let me go ahead and switch over to the. Hang on a second. I want to emphasize the strength of the analogy by comparing the arguments that I'm going to make here for Gauss's divergence theorem with, now this is literally taken right out of our lecture notes from arguments that we made developing Green's theorem. So with Green's theorem, does boundary circulation accumulate? With Gauss's theorem, does this outward-oriented boundary flux accumulate? Okay, well, fine. For this question, we looked at two regions, right, with a shared boundary curve, or you might say I took a big region and I sliced it in half. Here we're going to look at two solid regions with a shared boundary surface, right? And just as I did before, I'm going to write down, what is the boundary circulation around the whole thing. We'll go look at the boundary circulations around the individual pieces and ask, do they add up? What it, of course, boils down to is, do the terms associated to this shared edge cancel? Well, likewise, over here, we're going to look at these three individual boundary fluxes, and I'm going to ask, do these two add up to the boundary flux on the for that piece. And again, it comes down to looking at the shared, in this case, face. Right? Now let's think about what's going on that face. And here, let me zoom in so we can see better what's going on there. On that shared face, right? Thought of as part of the... let me make a better color choice. Thought of as part of the boundary of R1, right? The orientation we take is, well, outward. That's our convention, always outward. Okay. But now thought of as part of the boundary of R2, we have this solid region, that same exact face, in the way that it is part of the boundary of R2, well, outward from R2 is like that. Right? So, sure, we still have this face is going to show up twice in our, as we, write down all of our outward-oriented boundary fluxes, but that face is going to show up twice, but with opposite orientations. It's going to show up oriented to the right as part of the boundary of R1, but it's oriented to the left as part of the boundary of R2. And so those terms are going to cancel. And here's that cancellation explicitly right there. Right? So one orientation as part of the boundary of R1. Same surface, opposite orientation as part of the boundary of R2. And just like with Green's theorem, these two terms cancel and everything works out. Okay. All right. So I think the analogy is wonderful. I hope you all will spend some time looking at how the argument plays out. Now, it's geometrically different, of course, right? But it's morally kind of the same idea. The way this edge behaves versus this face when you're computing, circulation, counterclockwise circulation over there versus outward-oriented boundary flux over there. And it's, again, geometrically different, but extremely analogous. And when I wrote these pages, I deliberately, I took this page that I had written for Green's theorem, and I pulled it out and I had it on the desk next to me as I was, let me just make sure to keep the formatting as largely symmetric and kind of relatable, so that to emphasize how strong the analogy really is. Okay. All right, so let's see. Let's go back to Green's theorem. What was the next thing we did with Green's theorem? We asked the harder question. What if you do more slices? What if you chop it up, more dramatically? Right? Does it still work? Well, we're going to ask the same question here. It's a little bit harder to draw the picture. Right? Try it. It's very challenging artistically to draw, a solid that's been diced. Right? So sliced this way, and sliced that way, all three ways, right? As if you're, making little cubes, little cheese cubes, right? But you can still do this. And this is going to be a little tough to draw, but here's one little region, and here's another one of those little regions sitting right next to it. Now, where's the shared boundary face? Well, the shared boundary face is this right here. Right, shared boundary face. And I appeal to your geometric intuition for the same reason that this face, it's going to appear twice with opposite orientations, and therefore it cancels. Well, likewise, this little yellow face is, flux through that face is going to show up twice. Once as part of the boundary of the side on the left, once as part of the boundary of the chunk on the right. opposite orientations, cancels, and so that face disappears. And so just like every other example that we've seen, that face disappears. Likewise, this face disappears. Likewise, this face disappears. All of the interior faces that you make when you chop up this solid, they all disappear. The only faces that remain are the faces that were not in the interior. Namely, these faces out here on the sides. Does that make sense? Okay. All right. So, back to the sort of comparison mode here. Notice the strength of the analogy. I mean, here we're chopping up a two-dimensional region. Here we're chopping up a three-dimensional region. In all cases, those interior pieces disappear. So let's see here. I wanted to switch to that mode here. So here we were looking at circulation. Circulation becomes a sum of little circulations adding up over the interior. Likewise, here, now we're not looking at circulation, we're looking at flux. That becomes a summation of other fluxes, all the little fluxes adding up over the interior. Analogy, again, super strong. You start to notice, hey, this looks a lot like a double integral, except for there's no dA on the side, and so can I put a dA over there, and we did that whole thing where you can multiply and divide by delta A, and then you get an integral, and the question becomes, what's the integrand? Well, likewise here. Notice this looks a lot like a triple integral over this solid. I just need a delta V. Can I just stick a delta V on there for free? Well, not for free, of course. I have to, same concern that I had with Green's theorem. Let me go back to this. I can't just stick it on for free. I've got to, if I put a delta V there, I've got to divide by delta V to be free, to be legal, and that brings us to the question of what is this limit? If I look at a limit of boundary flux divided by volume. Right, so flux divided by volume. Flux per unit volume, you might say. That's what we come to. Okay. And so here it is. Flux per unit volume. Does this have a limit? Turns out it does. Yes, it does have a limit. Now, does it have a limit that we recognize from previous studies? Sadly, no. Right? Again, we were a little spoiled looking at the fundamental theorem of calculus. The limit that the integrand ends up being, it's like, oh my God, look at that! It's the derivative. It's our old friend. We already, not only do we know what that is, but we already know a bunch of stuff about it. And that was lucky, and it spoiled us a little bit. And you got to, let go of the need for something that you're calculating to be previously familiar. It's not a reasonable expectation, right? So we don't recognize this from previous discussion, but nevertheless, that limit, and here, again, reminder, flux per unit volume is something that can be computed. And I'm not going to go through the details here. I feel like it's a little bit in the weeds. I mean, certainly the point of view that I'm trying to give to y'all here in this lecture, the details of that calculation are not important. So you can just take this on faith, and here's what it is. It's that formula. All right, recall that the vector field. The vector field has components P, Q, and R. Right, so the x partial of the first component plus the y partial of the second component plus the z partial of the third component. And then y'all will now also recognize from way back when, section 15.1, y'all remember I complained a little bit about the book's point of view on, because they introduced the formula for divergence. In section 15.1, they just wrote down this formula. They said, hey, by the way, there's this thing called divergence. Here's the formula for it. With no context, right? No reason to believe, how am I supposed to think about this thing? What does it do? Where does it fit in, right? So I thought that was weird. But anyway, we now have a pretty reasonable point of view on that. And again, I've omitted the details, but this is how you should think of divergence. This is the point of view to have, in my opinion, is it's, in the limit, it's flux per unit volume. Think of flux just like circulation, just like change. Think of flux as something that accumulates. We compute flux, outward-oriented boundary flux. We compute it on the boundary. But it actually, honestly, it accumulates over the interior. It really is an interior accumulation. Just like total mass is the sum of all the little pieces of mass, outward-oriented boundary flux is a sum of a bunch of little tiny pieces of outward-oriented boundary flux. Okay, and so as such, this is a density. So this is quantity per unit volume, and therefore a density. Quantity of what? Well, flux. So therefore, flux density. It's a lot to digest, I know, right? So take your time, watch the YouTube channel, rewind, listen to parts again that maybe you didn't have enough time to digest the first time. That's by the way, the sort of the strategy of the course as I'm teaching it here is not that you will understand every single thing as we say it in class, right? But that if you take several passes, that you'll come to understand all of it. Okay. All right. So just going back to for the comparison purposes, again, I think this is really valuable. In the same way that we found ourselves looking at this, wondering what it was, realizing that there's a formula for it, and then interpreting it as a density. Well, same exact thing here. We found ourselves looking at something like that, different context, so different details, wanting to know, does that have a limit? Turns out there's a formula for it, and then we interpret it as a density. Right, so we're looking at flux, thus flux density, compared to previously we were looking at circulation, and thus circulation density. Okay, all right. All righty, let's see, and let's sort of put it all together. Again, the analogy is tremendous. And there's different notational choices that we make because this is a different context and there's different things that are therefore convenient. But the calculation summarizes in morally the same way. Let me go through that summary of the calculation. The quantity in question accumulates. Here we were looking at boundary circulation. Well, boundary circulation accumulates. Here we're looking at boundary flux. Well, boundary flux accumulates. Right? Multiply and divide by area over there to make this look like a double integral. Multiply and divide by volume over here to make this look like a triple integral. Asking what the limit of this is, turns out we have a formula for it, which we give a name to, namely Green's operator, which we interpret as circulation density. Likewise over here, what does this turn into? Well, it turns into divergence, which again you can write in different ways, and which we interpret as a density. So, really strong analogies. Okay, now some details. Let's talk about these notations a little bit. So this is the statement as I sort of derived it, as I motivated it, right? So a common rewrite of this is to take this vector surface integral, aka flux integral, and to rewrite it just for convenience. Look, it is called flux, and flux starts with the sound that phi starts with, and so people use capital letter phi to represent flux. Usually capital instead of lowercase, so it doesn't look like a spherical coordinate. That'd be weird, But anyway, so you can, that's what it is, and so you can just give it a name and call it that. Divergence, let me remind you, this is the sort of notational slang that everybody likes, myself included, for writing divergence. But in a lot of books, they don't want to use the slang, and they'll just say div. It's really a little bit more honest, I suppose. So anyway, this is how I often write Gauss's divergence theorem, but here's a completely acceptable alternative way to write Gauss's divergence theorem. Right? And so it looks different. It's really the same thing. Okay. And again, don't forget, what you're computing is flux, and therefore what you're computing it with can be interpreted as flux density. Okay. Is everybody on board? Let me pause for a moment for questions. Maybe somebody has a question. How we doing? Okay. All right. Okay. So let's see here. Now I skipped over something before I get into. Well, let's see here. Yeah, I want to go back a few pages. So I wanted to get into how the calculation goes. So reminder, we're talking about boundary object being viewed as an accumulation, an ensuing notion of an integral, and therefore a density. These were our details for our context. Specifically, we're looking at outward-oriented boundary flux. So I kind of glossed over this interpretation of what we're actually talking about here, and this is important for, if you want to use Gauss's divergence theorem to connect it to physical objects, physical things, right? And by the way, I know a lot of y'all are engineers. Apologies to those of you who are not. If you're not an engineer or a physicist, then think of this as, broad liberal arts education. You're going to learn about some stuff that maybe you don't have an immediate need for. That's a good thing, right? Anyway, so for engineering and physics applications, our vector field here, again, we're thinking of it as representing a flow of a fluid, right? And if you're thinking about it representing a flow of a fluid, then flux is quantity per unit time of fluid flowing through that surface, right? So that was our motivation for defining a flux integral in the first place. We've got this vector field representing a fluid flowing around, maybe the air in this room, right? It can blow, and the air is now moving that way. Well, here's a surface here. How much air did I blow through that surface? How many cubic inches, or pick your units, of air is flowing through that surface? Yeah, question.
This is like they used to calculate current in a river or something like that.
You totally could, yeah, absolutely. Yeah, it'd be a great application. So let's talk about that one. So if you were to put a, let's say, a net through a river, right, and you're just going to catch all the fish going through it, right? So you figure, well, if there's, one fish per 10,000 cubic meters of water, let's just say. Well, then you want to know how many cubic feet of water per hour are flowing through my net. Therefore, how many fish am I going to catch? Absolutely, totally. Okay, so let's think about how this applies then to if you're talking about a boundary region. And now let's not get into the accumulation business. So if you're talking about, again, if you have a net, I didn't draw that. I didn't think it through. Here we go. There's a net, and if your fluid is flowing through like this, then, well, the amount of fluid flowing through is, it's just the amount of fluid that's flowed through that, used to be on one side and is now on the other side, per unit time. But what if you're talking about a solid and its boundary surface? And again, you can still talk about flux, and here's a fluid. Let's suppose the fluid is flowing like that. Let's just say. Notice that on this part of the surface, on that part of the boundary surface, saying that the fluid is flowing through the surface is synonymous to saying that the fluid is flowing out of your solid. Right? Okay. Likewise, over here, and let's just pretend that the fluid is a nice, boring, easy, consistent flow like that. Keep in mind our orientations. And our orientation is always outward. Over on this side, looking at that part of the surface, fluid is flowing through the surface. Okay, wait a minute, but this time it's flowing into the solid, not out of the solid. But also, it's a negative flux, right? Look at the orientations, right? So these fluids, by virtue of flowing the other direction compared to the orientation, right? There's going to be a negative flux appropriate to the fact that it's going into the solid instead of out of the solid, right? So whether it's flowing in or out, flux through a boundary is telling you about the rate of change of the quantity of fluid inside of your region. Right? So it's a way of measuring how, water per unit time that's leaving the region, or, birds per unit time that are leaving this space, or, whatever. All right, so that's a nice point of view, and outward-oriented boundary flux. So another way to think of this object that we're, our quantity, our accumulating quantity that we're trying to keep track of and understand what it is quantity of fluid per unit time flowing out of the solid region. Okay. Quick pause for that. Anybody have any questions about that? Everybody good? All right. Okay. Right. Okay. So let's see. Where were we? Right. So let me remind you, we have these diagrams. We've seen these diagrams before. And by the way, I'm going to flip over. I have a better version of that diagram. This is, I went ahead and, made it look pretty, typed it up. Right? It's the same diagram. Doesn't quite fit. There's this business down here, but these are the lifetime theorems that we talked briefly about. We don't need to talk about those right now, so let me just do this. So this is our R3 diagram. By the way, there is also the two-dimensional diagram with Green's theorem and the fundamental theorem of line integrals. Again, we're not talking about that right now, so let me do this. So in 3 dimensions, here was the diagram chase for fundamental theorem of line integrals. We looked at a curve, we looked at its boundary points, we evaluated in the sense that we used this evaluation of some function on those boundary points. And again, let me just do that for an easier draw to get that. And then we asked, here, let me color code better. Then we asked, if I were to take that function, if I were to do something to it, is there something that I can do to it such that when I do this evaluation of the resulting whatever that is over the initial curve, that I would get the same thing? So is there such an operation? Is there something I can do that kind of makes both evaluations the same? And the answer was yes, and it was the gradient. So this is in some sense, again, the diagram chase of the fundamental theorem of line integrals. Taking a boundary and looking at change. Taking a gradient and looking at the line integral. Same thing. Recall with Green's theorem, we looked at a region, a two-dimensional region, and did the line integral. We looked at Green's operator of that vector field and did a double integral over the original two-dimensional region. Same thing. So the pattern's identical, right? And now notice for Gauss's divergence theorem, if you have now this, again, we're back in R3. this time a three-dimensional solid, look at its boundary surface, do flux of some vector field over that boundary surface. What we've found is that if we do the divergence of that vector field and take a triple integral of the divergence over the original solid, that we get the same thing. So the pattern again holds, right? It's an extremely strong pattern. All of these theorems, all of these big theorems that we're talking about in chapter 15, they all follow the same pattern. So again, it's really, I've mentioned this before, it's suspiciously analogous, and for good reason. It is because they are in fact all the same theorem. They are all special cases of this thing called the generalized Stokes' theorem, which is not something we're going to talk about in this class, but they all look alike because they are. So again, I think that's good to know. Okay, right. By the way, so having done, let's fill in the blanks on these diagrams. We've done the fundamental theorem of line integrals in 2 dimensions and in 3 dimensions, and then we did Green's theorem, and then we have now done Gauss's divergence theorem. We had a little digression talking about flux. But having done that, now we've done Gauss's divergence theorem, and you can probably guess what's going to come after Gauss's divergence theorem, right? It's the other box. Instead of, the relationship between dimensions 0 and 1, that is the fundamental theorem of line integrals, instead of the relationship between dimensions 2 and 3, that is Gauss's divergence theorem, we're going to find a relationship between dimensions 1 and 2. There's going to be a relationship between vector line integrals and flux integrals, specifically involving a surface and its boundary curve. And you can kind of fill in the blanks. You don't even really have to go through the argument to guess what the result's going to be. The result is going to be that if you take a surface and look at its boundary curve and do a line integral, and if instead you were to do what the diagram says, curl to the vector field, take then the flux over the original surface, you get the same thing. You can guess what the result's going to be, and we haven't done it yet, so let's not get too far ahead of ourselves. But anyway, I like to foreshadow, and I think it's healthy for you all to kind of have speculations in your mind of where you think it's going to go. Yeah.
Is this on the website?
Is what on the website?
This
no. This is from my textbook. But it's morally identical to this page that we have here. That's in the lecture notes. It's just a little easier to look at in the typed up format. So I figured I might as well use it. I got it. Might as well use it. Same thing here. Okay, pause again for questions. Is everybody okay? Any questions? How are we doing on time? Okay. All right. Am I fully zoomed? Yeah. Okay, so let's see an example. Let's suppose that I want to compute a flux. Quick reminder, if you want to compute a flux, you got options. Right? As of, before today's lecture, if you had encountered a problem that said compute a flux, you'd say, okay, I know how to compute fluxes. We parameterize the surface, and we, do the whole plug and chug with the pullback, right? You take the parameterization, you compute XU cross XV, that's your capital N, and then, et cetera. Okay. So let's compute a flux. Here's the vector field. Our surface is a sphere, right? Sphere, centered at the origin, radius 3. Now notice that this is not just, kind of what you would expect. This is specifically an inward-oriented sphere, which, by the way, perfectly fine. I didn't say boundary here. Boundary means outward-oriented. Sure, right. I'm not talking about a boundary, right? I'm saying I've got a sphere, and maybe I want to keep track of how much fluid is flowing in to this region, and if you want to know fluid flowing in, then you want the positive direction to be the direction that is pointing inward, and that would be inward-oriented. Right? So it's a perfectly reasonable question. An inward-oriented sphere is a perfectly fine surface through which you could want to compute flux. Okay, everybody clear on the question? Okay. How would you proceed, again, before today's lecture? Well, you'd parameterize. I advise spherical coordinates. Much better to parameterize with spherical coordinates in this case. You would parameterize with spherical coordinates. You would compute the two partial derivatives. You take the cross product. Then you would pause and say, hey, wait a minute. Did I parameterize this thing correctly or incorrectly? You would probably end up having parameterized it outward, because that's just how spherical coordinates works. And then you'd say, whoops, parameterized the wrong way. And then you'd put a minus sign, and everything's fine, and you proceed. And you'd have a long, tedious calculation of working out. It'd be a lot of trig. Look at this formula here, right? I mean, let me remind you that this vector field, you're thinking polynomial here, but it's not really. This is a polynomial with the understanding that x, y, and z are these spherical coordinate formulas. Rho, sine, phi, cosine, theta, et cetera, et cetera. So this x, this innocent, harmless-looking x right there, well, that's actually a bunch of trig. Right? So you've got a nasty vector field, really. And if you were to parameterize and do the slow, brute force, tedious plug and chug, it would be brutal. Okay, so let's instead see if we can use Gauss's divergence theorem. Let me go to the good diagram. Let's see here. So I want to use Gauss's divergence theorem. I've been asked to compute a flux. Gauss's divergence theorem allows me to compute a flux. There's a cost, there's an asterisk, as there are with all of the theorems that we've talked about. The asterisk is that flux has got to be through a surface that actually is a boundary of something, right? So that's the deal breaker. It's just like with line integrals. Green's theorem will not just let you compute any old line integral. The curve actually has to be Green's theorem. I'm looking at the wrong. Sorry. Here we go. Just like with Green's theorem, the curve actually has to be a boundary of some two-dimensional region. Green's theorem only addresses boundary curves specifically. Again, this is not a point of formality or rigor or something. You need to know that it's the boundary of a region, because you need to know that region. That's your domain for your double integral. Right? It doesn't make a bit of sense to talk about taking a line integral over just an open curve and claiming that's a double integral. Double integral over what? That's nonsense. It's garbage. Right? So be real careful about that. It's very common for students to write down in a situation like this. If I ask, compute a line integral, a lot of students will, just kind of be sloppy about it and say, line integral of, f dot dx. Oh, well, Green's theorem says that that's a double integral of Green's operator dA, and then let's suppose that maybe Green's operator happens to be 0, and they're like, oh, well, double integral of 0 is 0, ergo, the line integral is 0. Right? Garbage. 0 credit. I can't give any partial credit for this. The very first thing the student has done is to write down something that's nonsense. If there is no two-dimensional region, there is no double integral to be 0. There's no integrand because there's no integral. Right? Does everybody see how this is complete garbage if your curve is an open curve? Right? So likewise, and this happens every year. Oh gosh! And the reason I make a big deal out of it here in class is because I'm going to try to cut down as low as possible the instances of this happening. But if you are asked to compute a flux, one of these of some vector field. Right? And if that surface, let's suppose that this surface here is not a boundary. There is no anti-boundary. If you just kind of blow that off and say, oh, okay, well, yeah, that's a triple integral of divergence. And maybe you get lucky and the divergence is 0, or it feels lucky. It's actually super unlucky. Right? But if let's suppose it feels lucky, the divergence is 0, therefore the triple integral is 0, therefore the flux is 0. It's garbage. absolute garbage. If you're talking about a surface that's not a boundary, if it's just an open surface, like a rectangle kind of floating in space or something, it's not a boundary. There is no Gauss's theorem. There is no triple integral, therefore there is no integrand, and therefore the fact that divergence is 0 does not do what you think it does. So, big, dangerous landmine. Again, when the student does that, nothing they have said is true and relevant to the solution of the problem, and I can't give partial credit, much as I love it's my favorite thing when grading. Absolute favorite thing is giving points. Right? So, but I can't, because there's just nothing true and relevant on the page. So be super duper careful about that. So going back to this example, now, can I use Gauss's divergence theorem here? And, is this a boundary? I've got to ask if that is a boundary of something, and not really quite, right? It's the negative, though, of a boundary. Right? If I look at the here, let me color code better. This surface an inward-oriented sphere like this. That surface is a boundary. As the negative of the boundary of this ball. There's the ball. The boundary of the ball, I guess I'll do in green. The boundary of the ball is, there our solid ball. Boundary means outward oriented. Right? So our given surface is just like the boundary of the ball, but with the opposite orientation. Everybody see the color coding? You got to think through, boundaries are always outward, the given surface is inward. Other than this whole orientation thing, they're exactly the same thing. So the purple surface that I have is the negative of the green boundary surface that I like. Yeah.
So the reason that you couldn't say that the initial given surface was a boundary is because it was inward oriented?
Yep, that's exactly right.
So
boundary means outward oriented.
Okay.
Correction. Well, boundary surface means outward oriented. Yeah.
So you just have to make it negative so it can become your boundary?
Yep. That's right. And be careful how you say it. You don't want to abuse. But ultimately, it just comes down to a minus sign. But you got to say it, legally, right? Yeah. Right. So along those lines, we've been asked to compute this flux. That flux is, it's the negative of the flux through the boundary. There's that minus sign, right? It's the negative of the flux through the boundary. And so that green integral, the flux through the boundary, that's what I can actually compute, right? The flux through the boundary is something I can write with Gauss's divergence theorem. The flux through the boundary, being as it is a boundary, is a triple integral of divergence. And then it's all downhill from here. And I guess I'll pick up here next time. Let's see how we're doing. Yeah, that's fine. I'll finish up these details next time, but this is the most important part of that example. See y'all later. Have a good one.